So in our quest to find a scalable lock, we gradually refined the locks in previous videos and got to the cheese counter example, which was a fairly scalable lock. Right now we're going to try to improve that even further to get to scalability that suits hundreds and maybe thousands of threads. Our first example is going to be an improvement of the cheese counter lock. So just to refresh our memories, this was a cheese counter lock where we got to the counter, we got the next incremented ticket number, and then we waited until that ticket number appeared over the cheese counter saying now serving. And then we got into the critical section, and once we were done buying cheese, we simply incremented the now serving number to allow for the next one in line to get in there. For those of you who live in Sweden or has been in Sweden at least over one Christmas, you know that these kind of lines waiting for cheeses, waiting for delicacy, and most of all waiting in the liquor store tend to be longer and longer. And back a couple of years ago, even the liquor stores in Sweden had this kind of cheese counter ticket system where you pull the number and then you had to wait in line until it was your time to be served. So you got in there, you got your number, my number, and then you saw how far away that number was from the now serving number. And if it was like 500 numbers away, you went off and you did some Christmas shopping. And the amount of time you waited, you went off and did the Christmas shopping, it depended on how far off your number was from the now serving number. So if it was 500 numbers off, maybe you went off for 25 minutes, then you got back and so it was 100 numbers off, and then you went off for a shorter period of time. So this is some kind of controlled back-off strategy. Don't spin that closely until it makes sense. So instead of having 500 threads eagerly spinning to get in there, only the 10 or 20 or 30 threads that stand a chance at getting in there, they were spinning eagerly while all the other threads are out Christmas shopping. So this is what's called a back-off strategy. We call this one the ticket back-off strategy. There are other kind of back-off strategies. You can have an exponential back-off strategy. Just randomly choose a number. When you come back, if you're not being served, randomly choose a larger number based on the exponential back-off strategy to make sure that we don't want 1,000 threads eagerly spinning. We don't want 1,000 threads to get good news or to even just see that the number changed. Only want the ones that are stand a chance at getting in to see their number change. So that's what's called a back-off strategy. In this case, it's the ticket back-off strategy. Even less traffic at lock handover. That's what we're aiming for. So that is a fairly simple queue-based lock. What I'll do now is to explain to you a more sophisticated queue-based lock, and I choose to explain a lock that I designed myself many years ago, 20 years ago, called the CLH lock. And this is described, is compared and described with other kind of locks in a paper by Michael Scott in the papers directory of this course, which is mandatory reading. So even though I designed this lock many years ago, it's still very complicated. It's hard for me to understand what's going on in this lock. It's just 4 lines of code, and maybe you are better than me in understanding pointer-based kind of C code, but still it takes me a long time. So just bear with me when I try to explain what's going on here. So initially, each thread has 2 local variables, each of them containing pointers. Okay, and also initially there is one global cell in the shared memory. So these are global cells in the memory. And there's one of those cells in memory, and that's pointed to by both of these pointer variables. So the I variable and the P variable both points to this magic memory location over here. There is also another global variable, and this is one such global variable per lock in the system. And so each lock is also a pointer. It doesn't contain a value, it really contains a pointer, and that pointer points to another memory cell in memory. And both these cells, what the pointer for when either lock is pointed to, as well as the two local pointers from each thread is pointed to, those cells are initially set to 0 for idle locks. The line of thought about how you implement a lock based on this kind of structure is a three-step process. First, what you do is you initialize the lock that the I pointer flag is pointed to busy. Well, the P pointer flag is also pointed to there. So you initialize it to 1, which is busy. Okay, done. We've done that. The second step in order for you to get to acquire the lock is to atomically swap whatever L is pointed to and whatever P is pointed to. So P is pointed to this cell, we now just initialize to busy, and L may be pointing to a cell which says busy or may say free, depending on what the state of the lock is. So atomically, we're going to make this swap. So we're going to make this thing. So now L is pointing to busy, to a cell that says busy, and P is pointing to whatever L said before. And the third step here is when you wait until whatever P is pointing to is equal to 0. Well, right here, L was initially free. So this will be good news for this lock. We will actually be able to acquire this lock right away. This is how you would implement this lock. First step, set whatever I is pointed to busy. Swap whatever P is pointed to and whatever L is pointed to, and set whatever L is pointed to whatever P is pointed to. So this is just one of these atomic swap operations discussed when we initially talked about synchronization. And then we say, while whatever P is pointing to is not 0, keep spinning. Okay. So that's the quite lock. So this is 3 lines of code, and it's hard for me to figure out what's going on here. I still always have to write these kind of comments to figure out what's going on. And the way you unlock it is to release the lock, you write a 0 to whatever I is pointing to. So whatever I is pointing to, you write a 0. And then you make sure that I and P are pointing to the same thing again, just to get into the same initial state as you had before you started to use the lock, just to enable you to use the lock again. So here is a picture of what would happen if 3 different threads wanted to get into the lock one by one. So initially, L is pointing to memory location, which is 0, so lock is free. And the first thread wants to get into that lock, so we perform the first operation. Okay, initialize whatever they're pointing to 1. Then we do the second operation, the atomic swap. So here we have the atomic swap. Now L is pointing to, once more, point to the lock, but it's pointing to busy lock. And P is pointing to free lock. And then we say, while P is not free, keep spinning. Well, P is free. P is pointing to a 0. So this thread will manage to get into the critical section. It will do automatic stuff in the critical section. While it's in the critical section, the red thread wants to get into the lock. So it will perform the same operations using its data structures. It will set its magic memory location to 1. It will do an atomic swap, and then we'll keep waiting while whatever p is pointing to is not equal to 0. Well, that's bad news. The lock is busy now, so it will keep spinning there. So it will in while p. And of course, the gray thread also wants to get in there, performs the same operations, and now gray thread is spinning on one memory location to wait for it to see 0. Red thread is spinning on a different memory location, waiting for it to see the 0. And the yellow thread is not spinning anything, it's happy in the critical section. And what you see here is part of the magic of this operation, that each thread, instead of all threads spinning on one variable, whenever it changes value, lots of coherence activity will happen. Each thread now spins on one and only one value. And that value, and all in that value, is only changed by the predecessor in this queue. So talking about the number of coherent operations that needs to happen is that this thread needs to change one value that only another thread is waiting for. And once that is changed, all the gray thread has to do is to read that value. So compared with the previous algorithms, it's a like 2 coherence transactions to make this happen. Here is 1 coherence transaction to get write permission to a shared variable, and after that, after that value has been invalidated in the gray thread's cache, all it needs to do is a single read transaction. So this is sort of order of 2 transactions to perform this, even though getting into the lock is slightly more complex. Releasing the lock is quite simple. You just write a 0 to whatever I is pointing to. So when the yellow thread wants to do that, it writes 0, and then it makes sure that I and P are pointing to the same thing again, just to get into the initial state. So it's a single write operation, and so forth. Releasing the red, releasing the lock, same thing. The gray releasing the lock, the same thing. So it's very simple. It's few operations. There are more atomic operations going on, so more heavy-handed atomic operations. So the overhead for non-contented locks is too high, but for contented locks, this is a really good idea. So let's look at the performance numbers. How do these locks perform? We missed a transaction here, a question. How many bus transactions between exit critical section until a new critical section entry do we see with this kind of locks? And once more, I try to make the numbers here. Is it the order of between 1 and n transactions? Is it just 2 transactions, or is it more of the order of n transactions? So fortunately, I already gave this one away while I was talking here. It's 1 invalidate and 1 read to share. So it's a very, very cheap transaction handover. Looking at performance numbers, comparing all these numbers. So here we have the pound transaction where we only had the test and set. We didn't have any local spins in the caches. We added local spins in the caches. We have the ticket, the cheese counter operation. We have the ticket with the back off. So that's the Christmas algorithm. And then we have this funky kind of pointer whistling operation, which is called the CLH algorithm. You can see from this that maybe CLH is slightly better than the spin, but it's all dwarfed by how bad the pound transaction algorithm is. So taking the pound away, we get a better look at what's going on. So going up to 12 threads here, we can see that we started to get a little bit of a penalty here from the spin, and then we have the ticket with it, which is better. Ticket back off is looks like it's better, and sometimes it's even better than CLH, but this is a little bumpy. There, these are real numbers from the real machine, so it's going up and down a little bit. if we're really going to see the benefit of this, we have to move beyond just 12 threads. So what I'll show you here to you is a system which is much larger. System we have some large number of CPUs inside a box. This is an oldish technology. Think about this as some number of threads inside a multi-core. So think about this as a multi-core, and then several multi-cores are connected together with a kind of interconnect. So this kind of the QPI interconnect, for example, and then you have some number of threads inside some other multi-core, and this is how you build your system. This is what called the NUMA kind of system. So here it's cheap, as long as you have keep coherence inside a node, but once you need to read data from somebody else's cache that's not in your node, it's much, much more expensive. So we have typically this implemented by the not the scalable Snoop implementations we discussed down to some gory detail so far, and this other coherence between all these multi-core chips is done through what's called directory coherence, which is takes substantially much longer time. So performance difference between staying inside a node and going between nodes is, in this example on the specific system we measured here, is 6 times remote access compared with the local access. That varies a lot. Maybe between 3 and 6 would be a good number. So let's see how the different blocks perform in this more scalable system. We can get much beyond 12 threads. So here we see the spin. This is not the pound. This is the spin lock. How the spin lock performs on this more scalable system, and you can see it starts to go through the roof. So this is the optimistic or pessimistic test and set operation that we before were so proud of, and it starts to really take off on this system going through the roof. We have a version of a spin lock we haven't talked about, where you have a spin with exponential back off, performs much better. We have the CLH lock, which is Q-based locks, and there's another lock proposed by Miller, Crown, and Scott, the one who wrote the paper we have in the course directory, and it's really comparable to the CLH lock. However, you can do better than this. By the way, this is the benchmark that we did. This is artificial benchmark. This is no real application. It's just how quickly can you get into the lock. You just get into the lock, you increment some share data structure, and then you get out of the lock. So can you do better than this? Well, one of my former students, Zoran Radovic, came up with a new solution. Said, Q-based locks are good, but they are too fair. We don't like the fairness. So what's bad about fairness? Well, first come, first serve is fair, and people in Sweden like this. We need to be fair. But it would be better actually for everybody if we were less fair. How about, instead of giving the lock to whoever has been waiting longest at the cheese counter, you give the lock to somebody else in your neighborhood. You give yourself to somebody else in your same multi-core. So I already told you that there is a performance penalty. It's so much quicker to communicate with somebody in your own multi-core. So if you give the lock, if you are unfair and give it to somebody in our own multi-core, the handover of the lock will be faster, but also the critical data structure that we're protecting is more likely to be in a cache in that multi-core. And if we can do a cache-to-cache transfer inside the multi-core, it will be much faster. And that's what Zoran leveraged. So what he showed here is compared with other locks, spin exponential, MCS and CLH locks. This is the one we looked at some gory detail. His own lock, when you increase the number of processors, is much, much better. So what's happening here is the secret sauce he reveals in this slide graph to the right. He shows what's the likelihood that a lock that I release will be transferred to a different node, to a different multi-core. or will it stay in the same multicore? And since he had an implementation that was promoting unfairness, he wanted to promote his neighbors. The likelihood that his lock had to jump to a different node stayed down at a very controlled number, 5%. So he designed this lock to be unfair 20 times. When he'd been unfair 20 times, he forced the lock to go to somebody else. So he was shooting for this number 5%. And the other locks, actually the Q-based locks, they should go towards 50%. And I have very poor explanation why they're not going towards 50%. These are two nodes, two multi-cores, and of course the likelihood that you should go to the other node should be equal to very, very close to 50%. It's not. An interesting point here is the spin lock is actually, even though it wasn't designed to be unfair, just because Murphy has been involved, it turns out that it's the most unfairest for this point right here. And that's why its performance is actually quite good at this point. So for 4 processors, just happens to be that all the latencies of handing over and transactions and all that, it works out in its favor. It's being, even though it wasn't designed to be so, it's actually very unfair, and that helps its performance. Looking at the real applications, so this is one real-world application from a benchmark suite called Splash 2 actually, and the application is called Ray Trace. If you compare all these locks, so we have the spin exponential, MCS, which is Q-based locks, CLH, which is also Q-based lock, the one we looked at, they all, once you get beyond 8 or 12 processors, see performance degradation due to lock contention. It's a critical region, it's dominated by it's dominated by this critical region, and since the overhead of handing it over is so high, they lose performance. So the Zoran's algorithm, the RH algorithm, actually managed to not just go flat, but actually still get some performance above that. And then he designed yet another algorithm for a different conference, and that managed to do slightly better. So contrary to what your mom told you, being unfair is not always a bad thing. So in summary, looking at all these different kind of implementations of synchronization, if you look at the time between entering into critical section, how that is affected by contention, we have the test and set algorithm that, it's good, 2, 4, 6, it's but then it fairly steeply goes up. We have the test and set with exponential backoff, that's better. We have the Q-based locks. They have actually, for non-contended locks, it's more complicated to acquire lock, and so we have some complication that's not needed, and that adds some overhead for non-contended lock. But once you get into contended lock, it's actually constant time. Doesn't depend on n. The constant time is proportional to some constant factor times 2. So regardless of how many threads you add, it's roughly the same. And then we have the magic lock by Zoran, which is a lock that the more contention there is, the better it performs. Because the more contention there is, the more likely you are to find somebody else within your same multicore which is interested in the lock. So you can hand it over to that thread quicker. So the handover is quicker the more contention it is, because the likelihood goes up that you will find a friend in your same multicore. So more recent, there's a PhD student at the department in the compiler language group who is drafting a paper and submitting a paper which is on an even more scalable synchronization primitive. So this is a primitive that is actually not as unfair as Zoran's primitives, but he has been looking at different kind of properties, and we are keeping our holding our breath and hoping that this will make one of the best conferences. So stay tuned for more information about that.